Hi, in this video we are going to talk about Hamiltonian path, so let's get started. And let's talk a bit about traveling salesman problem, or TSP. Given a list of cities and the distances between each pair of cities, what is the shortest possible route that visits each city exactly once and returns to the origin city? It may sound familiar to you because we have to find the Hamiltonian cycle again. And we have discussed in the previous videos how to solve a Hamiltonian cycle, but we were considering small graphs. It is an NP-hard problem, so for small subproblems, few cities, we can solve it with backtracking, for example, as we have seen. But if n is very large, for example, n is the number of vertices in a graph or the number of cities, whatever, we have to use heuristics. Because for n cities, we have n factorial possible solutions, so the solution space is enormous. We are not able to solve it in a brute force manner. We are not able to solve it with backtracking because there's lots of possibilities. So we have to use heuristics. What are these heuristics? Usually for NP-hard problems, we are looking for an approximate solution instead of the exact one. So we come to the conclusion that, okay, these problems are very hard to get an answer. But maybe if you are looking for just an approximate solution, not the exact one, maybe we are able to solve it in polynomial time. And yeah, we come to the conclusion that if we use these so-called heuristics, such as ant colony optimization, genetic algorithms, or simulated annealing, we are able to solve its problem. On the other hand, it's not going to be an exact one, it's going to be an approximate one. So it's not the global optimum, but it's not far away from the global optimum. These ant colony optimization and genetic algorithms, if we try to mimic nature, for example, genetic algorithms mimic the nature of gene expressions, and in the course of time we keep getting better and better elements, better and better solutions. For example, as far as the traveling salesman problem is concerned, we keep better solutions. So we visit every city exactly once in the shortest path manner. Simulated annealing is my personal favorite as a physicist because the easy model, the mathematic model of ferromagnetism relies heavily on this technique. So we have a so-called T temperature parameter, and at the beginning T is large. We consider bad moves or suboptimal solutions too. I think it's pretty counterintuitive because we are trying to get the optimal solution. Why would we take into consideration bad moves? Because it helps us to avoid local optimums. So we decrease T as the temperature parameter and we keep discarding bad moves. And it is going to converge to an approximately global optimum or global solution. This is a good illustration of simulated annealing at Wikipedia. If the temperature is high, we consider bad moves. But if the T getting lower and lower, we stuck on the global optimum, as you can see. We keep getting better and better solutions, and that's why we are able to avoid local minimums. This function has several local minimums, and it has a single global optimum, the maximum value, and we are able to find it with the help of this simulated annealing. So I don't want to repeat myself over and over again, but it's very important that if we have an NP-hard or NP-complete problem, we are not able to solve it exactly in polynomial time. We do not have algorithms. If we will have quantum computers, okay, we will be able to solve it, but not yet. So, okay, what's the problem? That we are not able to solve it. Maybe if we are looking for approximate solution, we are able to solve it, and that's why the heuristics came to be, such as the simulated annealing. Thanks for watching.